This video will cover the first half of the notes for the fourth lesson in the matrices unit of finite math. It covers what is an identity matrix and how to find the inverse matrix of a 2x2 matrix if one exists. So we will start off this video by describing an identity matrix. Now that involves us to understand the word identity. We have, throughout various levels of math and with various skills, this idea of an inverse and an identity that pop up over and over and over again. For instance, in addition, when we look at addition as an operation, we have, every number has an additive inverse, and there is a number that is the additive identity. So an additive inverse is a number that when you add it to a, like say 3, the additive inverse of 3 is negative 3. So additive inverse, for the inverse in addition, additive inverse, is the opposite. This is because when you add 3 and negative 3, the result is 0, which is called the additive identity. It's called the additive identity because if you take a number like 3 and you add the identity, 0, 3 plus 0 is still 3. So an identity is something that does not change value. So I, the identity matrix, which can be any size, but it has to be square, is a square matrix where each element on what is called the main diagonal which is from the top left to bottom right corner. Every single element on that diagonal is a 1. All other elements in the entire matrix are zeros. So in a 2x2 matrix, the top left and the bottom right would be 1s, and the other two entries would be zeros. In a 3x3 matrix, the top left would be a 0, the rest of the first row is 0. Or top left would be a 1, the rest of the first row is a 0. The middle entry in the second row would be a 1, and the bottom right entry would be a 1. So that entire diagonal from top left to bottom right would be 1s, and every other entry is a 0. Now we could continue this exact same pattern for any size square matrix. For instance, here is 4x4. Notice the entire top left to bottom right diagonal is 1s, and every other entry in the entire matrix is a 0. Now the reason this is called the identity matrix is because our main operation with matrices is matrix multiplication. And when we multiply any matrix by the identity matrix, it will return the exact same matrix. Nothing will change. So when we multiply I times a matrix, say A, the answer will be matrix A. So it doesn't change the value. Just like when we take 3 and we add 0, it's still 3. That's why 0 is an identity. Alright, on to inverses. So two matrices are called inverses, and by the way, inverse matrices only applies to square matrices. If it's not square, it doesn't have an inverse matrix. So two square matrices A and B, are inverses if and only if A times B is equal to an identity matrix and B times A is equal to an identity matrix. Notice how many times I'm underlining and. Those both have to be true. A times B has to equal the identity matrix I, and B times A has to equal the identity matrix I. Now, it is not something you're going to have to be able to do by hand, find the inverse matrix. You're not going to have to do that by hand anymore, unless it's a small matrix, like a 2x2. So there is a rule for that. The rule for finding the inverse of a 2 by 2 matrix just requires us to come up with an abstract 2 by 2 matrix. So let's say we're starting off with A. So if A is equal to the matrix A, B, C, D, then the inverse of A, notice the notation, if we put A to the negative first, that means the inverse of A, is equal to the scalar product of 1 over the determinant of A times the matrix D, negative B, negative C, A, which is the first matrix rearranged slightly with a couple of sign changes. So we do 1 over the determinant of A, which is why we did the determinant first, times, and we switch. Notice the top left and bottom right have switched locations, and the top right and bottom left have their signs changed, but do not change locations. So if we look at that and we ask ourselves, all right, it says in the directions if 1 exists. So there's got to be a situation where there isn't an inverse. So what about this equation could result in there not being an inverse? Depending on how good you were at Algebra 2, you may notice that this fraction has a variable in the denominator. And you may remember from Algebra 2 that if there's a variable in the denominator, that variable's value cannot be 0, because you cannot divide by 0. So this question at the bottom that says, when does a 2 by 2 matrix not have an inverse? That would be when the determinant equals 0. I don't know why I'm trying to spell 0 with an S. There we go. And the reason why that would be is because you cannot divide by 0. So finding the inverse of a 2 by 2 matrix is one of the major skills in finite. We need to be able to do it flawlessly every time. So we're going to do about 5 examples of this, and then we'll call it a video. So on this next slide here, we have a couple of matrices, A and B, and C, as it turns out. And we're asked to find a matrix, an inverse of each matrix if they exist. So again, we have a rule, so let's rewrite the rule. Actually, I'm going to rewrite the rule. You shouldn't need to, because it should be right there in front of you. If A is A, B, C, D, then the inverse of A is 1 over the determinant of A times D, negative B, negative C, A. So basically, this is going to turn into a 3-step process. You are going to start by finding the determinant of the matrix. So let's say determinant of matrix A, which is 6 times 4 minus 10 times 2. And we're not going to go over why that is, because you should know from a previous lesson. That is 24 minus 20, or 4. So there is an inverse, because this is not equal to 0. So next we go to writing the inverse, which would be 1 over the determinant, which is 1/4. That goes in there. We're going to switch the 4 and the 6, and we're going to change the signs on the other two numbers. So -2, -10. Then we have to carry out this scalar multiplication and multiply each number in the matrix by 1/4. So that would be 1, -1/2, -5/2, and 3/2. Each of those numbers is a result of doing 1/4 times that element and then reducing the fraction. That is the inverse of A. Notice the inverse is the same shape as the original matrix. Okay, on to the next one, the determinant of B. That would be -3 times -6 minus 2 times 7. which would be 18 minus 14, or 4. So once again, there is an inverse. So the inverse of B is 1 over the determinant times, switch the -3 and the -6. Their signs don't change, they just change locations. Change the signs on the 2 and the 7. Their locations don't change, their signs do. Then we carry out scalar multiplication by taking each of these numbers times 1/4 and reducing. So that would be -3 halves, -7/4, -1/2, -3/4. And that is the inverse of B. C is the first time we run into the special case. If we do the determinant of C, we'd get -3 times 4 minus 6 times 2. Oh, -2. 6 times -2. That would be -12 plus 12, which is 0. We said earlier, if the determinant is 0, no inverse exists. And again, the reason for that is the determinant of C is equal to 0. So as soon as we see a determinant of 0, the problem is over. We write there is no inverse. Let's do a couple more. The determinant of matrix D is -2 times 6 minus 5 times 0. That would be -12. That means there is an inverse. So we say, okay, that's 1 over the determinant of D, which is -12. We're going to take the -2 and the 6, and we're going to switch their locations. We're going to take the 0 and the 5, and we're going to change their signs. Now 0 doesn't have a sign, so changing its sign doesn't affect it. It's still 0. 0 is not positive or negative, so you can't switch its sign. So you just leave it alone. It just stays there. Then we're going to carry out that scalar multiplication by multiplying each of these numbers by 1 over -12 and reducing. That would be -1/2, 0, 5 over 12, and 1 over 6, which would be the inverse of matrix D. Finally, on matrix Y, the determinant of Y is 9 times 4 minus -6 times -6. That is 36 minus 36, or 0. We already discussed this. That means that no inverse exists because the determinant of Y is equal to 0. That does it for finding the inverse of a 2 by 2 matrix and our introduction to the idea of an identity matrix.